Welcome viewers to the third segment of the sixth lecture for the online series of lectures for the course of Algebraic Topology 1. In the previous segment uh, we learned the definition of a simplicial complex and and we have also seen that simplicial complex being the union of simplices can also be considered as a subset of R to the n, right? But we did not give any topology to such a simplicial complex. So we'll begin this segment with this concept of giving topology, and so that this simplicial complex becomes a topological space. So let us get started with this definition. Let mod K be the subset of R to the n, that is the union of the simplices of the simplicial complex K. Okay, giving each simplex its natural topology as a subspace of R to the n. We know that each simplex sigma is a subspace of R to the n. So we can equip that simplex with its subspace topology inherited from R to the n and make it a topological space. Okay, and that way we then topologize mod K by declaring a subset A of mod K. Okay, mod K is the union of all those simplices of the simplicial complex K. Okay, and then we take an arbitrary subset A of mod K and call it open. Sorry, we call it closed if and only if A intersected with sigma is closed in sigma. Okay, so first of all we give each simplex in mod K the subspace topology that it inherits from R to the n. Okay, then we take any subset A of mod K and call it closed if and only if A intersected with each simplex is closed in sigma, in that simplex sigma. Okay, and this happens for each sigma in the complex K. Okay, the space that we denote by mod K, the topological space, is called the underlying space of the complex K, or the polytope of K. Okay, good. In general, in general, the topology of mod K, okay, which is also called the underlying space of the complex K, is finer. Okay, when I say finer, I mean that in this topology there are more open sets than the topology mod K inherits as a subspace of R to the n. Okay, see that this mod K, this is first of all a set, the union of all the simplices of K, the complex K. Okay, and since each sigma is a subspace of R to the n, this union of all those simplices as a set is a subset of R to the n as well. Okay, so being a subset of R to the n, this guy is also equipped with the subspace topology, that it inherits from R to the n. But that topology is coarser than the topology that we have defined in this paragraph. Okay, meaning that to phrase it in other way, the topology that we described in this first paragraph is going to be finer. In other words, in that topology there will be more open sets compared to the topology of this set being a subset of R to the n. Okay, or this set, or the topology that this set inherits as a subspace of R to the n. Okay, good. So let us see this fact in detail. So there are two topologies on mod K. Okay, the union of all the simplices of the complex K. Okay, one topology is the topology that we defined earlier. So whenever I say that the topology of mod K, I mean that topology, the one that we defined in the first paragraph. Okay, and the subspace topology that this guy inherits from R to the n is the other topology. Okay, all right. So if A is closed in mod K, okay, in the subspace topology, then we are going to show that this guy A is also closed in mod K in the other topology that we defined in the first paragraph. Okay, then according to the definition of subspace topology, to the definition of subspace topology, A is equal to B intersected with this set mod k. Okay, mod k is a subset of R to the n. Okay, where this guy B is a closed set in R to the n. Okay. Now each sigma, each simplex sigma in K is of course contained in R to the n. Okay. So we have taken B to be closed in R to the n, right? Now, since B is closed in R to the n, B intersected with sigma B intersected with sigma is also closed in sigma. In the subspace topology, sigma inherits from R to the n. Okay, hence this guy A equal to the intersection of B and mod K is also closed in mod K, establishing the fact that the subspace topology on mod K inherited from R to the n is contained in the topology of K, of mod K defined earlier. Okay. All right. So which means that the topology of mod K defined earlier is going to be finer than the subspace the subspace topology mod K inherits from R to the n. Okay. All right. So let me erase everything. The two topologies on mod K are in general we have seen earlier that one is finer than the other, and in fact they are in general different. Okay, as we'll see in the examples, right? We will see a couple of examples showing that these two topologies are in general different from each other, as we will see using examples soon. Okay, In fact, if the underlying complex K is finite, okay, in that case they are the same, they coincide with each other. All right. So the containment in the other direction needs to be proved to prove that they are the same in the case when K is finite, right? So let's do that. Suppose K is finite and A is closed in mod K in the topology that we defined earlier. Okay, in that topology, A is closed in mod K. Okay, we are starting from that topology. Then, according to the definition of this topology on mod K, A intersected with sigma I is closed in each sigma I. Or this guy is closed in sigma I for hi in this finite set 1 to all the way up to n, with mod K being the union of all these simplices, right? I from 1 to n. Okay. Now A intersected with sigma I is closed in sigma I for hi, and sigma I is closed in r to the n for hi, right? Hence, so there is a lemma in the point set topology book by Moncrief, okay, titled Topology. So there is a result in that book by lemma uh, uh, under lemma 16.2, lemma 16.2, okay, where this version of the result holds for open sets. So there one can also prove that results for closed sets. Okay, so let me write it here inside the bracket. Same result holds for closed sets. Okay, so I leave it as an exercise for you. You got to prove it. So so A intersected with sigma I is closed in sigma I. That follows from the definition of this topology on mod K. And each sigma I is closed in R to the n. So using that result for closed sets, we see that um, A intersected with sigma I is closed in R to the n. H A intersected with sigma I is closed in R to the n. Okay, now since A is contained in mod K, okay, mod K being the union of all these simplices. Okay, and we started with the fact that A is a subset of mod K, which means that A is contained in this union, right? One therefore has A is equal to the union of all these intersections, okay, from I to N. Now each of these sets in this union is closed in R to the N. We know that from the definition of the given topology on mod K. Each of this is closed in R to the N. Okay, that we have seen here. Each of these sets is closed in R to the N, and we know that finite union of closed sets is again closed. Okay, and hence this guy A is closed in R to the N, right? So we have reached the conclusion that A is closed in R to the N. As A is contained in mod K, A is equal to A intersected with mod K, right? And we have seen earlier that this guy A, sorry, this guy A is closed in R to the N, okay, which means that A is closed in mod K in the subspace topology inherited by mod K from R to the N. Okay, so that this way the other direction of containment has been proved earlier for the general case where K can be infinite as well, and for this direction, using the containment in this direction for the case when K is finite, we see that these two topologies are indeed the same for the case when K is finite. Okay, good. Now the examples that I talked about earlier, I need to give you examples on these two topologies in a that we can put on a simplicial complex. Okay, this is example 1, topology on mod K. This is just a notation. Mod K doesn't have to do anything with the modulus of K, something like that. Okay, doesn't make sense. It's just a notation. Let K be, let me define the complex first. Let K be the collection of all one simplices, okay, simplices in the real line of the form m comma m plus 1, these closed sets. We take all such closed sets in R. These are one simplices, okay, where m is an integer different from 0, integer different from 0, along with all one simplices of the form 1 over n plus 1 to 1 over n, where n belongs to the set of positive integers. Okay, this is how we denote positive integers. Okay, starting from 1. In other words, it's the set of natural numbers, the set of all positive integers. Okay, good. So let me picture this here. So this is 0, this is 1, this is 2, this is 3. On the other direction we have -1, -2, -3, and so on. Okay, so we take all such unit intervals of length 1, all these intervals, these intervals are of this type, m from m to m plus 1, where m is any integer different from 0. Okay, so it does not tell anything about this interval from 0 to 1, right? Because m cannot be 0. So for this part we rely on these intervals. So one example is, for if I plug in 1 here, I get 1/2 to 1. Okay, this is contained here in this interval from 0 to 1. Okay, 1/2 to 1. Okay, and then we can have 1/3 to 1/2, right, which is something like this, 1/3 to 1/2. Okay, this way we can have all these, all these small intervals sitting next to each other contained in this interval 0 to 1. Okay. So now we have a collection of these one simplices here. Okay, and now the claim is that um, the set 1 over n, where n belongs to the set of positive integers, okay, which means that this set is something like this: 1, 1/2, 1/3, 1/4, 1/5, continuing like this. This is an infinite set. So this set is closed in K, where in mod K, where mod K is the union of all these one simplices. Okay, so the claim is that this infinite set is closed in mod K in the given topology. Okay, but we already know that this set is not closed in so what is mod K? What is the underlying space in this example? The underlying space is R. Okay, this is the polytope in this case, and this underlying we all know that such a set is not a closed set. A, you know, in subspace topology induced from the topology of R. Okay, in the subspace topology that the union of all the simplices inherits from R. Um, this set is not a closed set because it has an accumulation point being 0, and that accumulation point is not contained in this set, and hence this set is not closed. Okay, all right, now let's see this thing into further detail. The set 1 over n, as n varies in the set of positive integers, is closed in mod K, since 1 over n and belonging to the set of positive integers, this set intersected with 1 over m plus 1 to 1 over m for some positive integer m. Okay, for some, so we take some positive integer m and form this closed interval in R. Okay, and that getting intersected with this guy is just and that is just the union of the two endpoints, 1 over m plus 1 and 1 over m. Okay, okay, and now the claim is that this 2-point set is is uh, is closed in the subspace topology inherited from R. Okay, um, so let's see how we do that. Now 1 over m plus 1 is easily seen to be closed in this subset of R, 1 over m plus 1, 1 over m. Okay, why? Because 1 over m plus 1 comma 1 over m is open in this subset of R. Okay, so this guy, so this since the complement is open in the given set, the 1 over m plus 1 is closed here. Okay, and similarly one can show that 1 over m is closed in this set 1 over m plus 1 to 1 over m. Okay, so the union of two closed sets is again closed. Therefore, the union of these 2 points, or the union of these 2 singletons is closed in this set 1 over m plus 1 to 1 over n. Okay, in subspace topology inherited from R. Okay, good. So this is what we needed to show. Now also this the set that we are concerned with, okay, 1 over n such that n belongs to the set of positive integers. This set intersected with 1 comma 2 is equal to the singleton 1, which is closed in 1 comma 2 in subspace topology inherited from R. Okay, good. And 1 over n with n belonging to the set of positive integers intersected with other closed intervals is empty for all m in the set minus 0 comma 1. Okay, which means that all integral value of m different from 0 and 1. Okay, and those sets intersected with the given set is the null set. Therefore the set 1 over n, where n belongs to the set of positive integers, is closed in, because this guy is closed, right? The empty set is always there in the, the empty set is both open and closed, and so which proves that from the definition of the topology on mod K, this set is closed in mod K. Okay, all right. Now this set intersected with mod K is going to be equal to simply this set, right? 1 over n, as n varies in the set of positive integers, since this set 1 over n is a subset of mod K. Mod K is the union of all those one simplices or closed intervals in R that we discussed earlier. Okay. Now, since the accumulation point or the limit point, if you want to call it, of the set 1 over n is 0, okay, which does not belong to this set. Okay, since the accumulation point does not belong to the set 1 over n is not closed in R. Okay, which means that in other words, this set 1 over n is not closed in mod K in subspace topology inherited from R. Okay. All right. So this way we see that these two topologies on a that one can put on a simplicial complex can be different. Okay. Now our second example is about one simplices in R2. Instead of R, now our ambient space is bigger. Okay. This is R2, and let me define. Let K be the collection of all one simplices sigma 1, sigma 2. Okay, this way it keeps continuing, where each sigma I is the one simplex having vertices. So there will be two vertices of this one simplex having vertices 0 and 1 comma 1 over I. Okay, so if this is 1, this is 2, then this is 3, and this way we have 1, 2, 3, and so on, so forth. Okay, so I think we can make the picture a little bigger. So let's call it 1, and then we have 1 here, 2 here, like this. Okay, so this is the point 0, and when I is 1, then we have the other point here. Okay, these 2 points. So this is a one simplex. This is 0 comma 0, and this is 1 comma 1. Okay, so where is the second simplex? The second simplex, this is one of the vertices of the second simplex, and the other vertex is 1 comma 1 half, which is here, right? So this is the second simplex, and then we have 1 comma 1/3, right, which is here. This is 1 comma 1 half, then 1 comma 1/3. Okay, and keeps continuing like this. Okay, so this is the picture of the one simplices in the ambient space R2. Then one can see that K is the collection of all these one simplices. Okay, then K is a simplicial complex because two simplices, it satisfies both the properties that a complex should satisfy. So two simplices in this complex intersect only at the point 0, and 0 is a face of those two simplices. So K is a simplicial complex. Okay, the intersection of mod K so now I draw a parabolic arc. It goes through 1 comma 1 like this. Okay, so the intersection of mod K with the open, which means that this point 0 0 is not included, with the open parabolic arc x comma x square in R2 such that x is strictly positive. So this means that it's an open set, right? Well, I shouldn't say open, it's it's should not say open. It's an open parabolic arc. Let's put it like this. This guy, the intersection of mod K with this guy is closed in mod K. The set so this is a collection of all ordered pairs like this: 1 over I comma 1 over I squared, all these ordered pairs such that I is a positive integer. Okay, intersects a given one simplex a given one simplex x comma x over m. Okay, you see that this is the equation, parametric equation of this straight line joining any 2 points here. So we can pick up all these points, so that forms a set. So pick up any ordered pair from that set and join it with the vertex. The line that you get is given by this this ordered pair, meaning that this ordered pair gives any point of that line. So x comma x over m is in R2 such that x is positive or 0, right? X is greater than or equal to 0, right? So this set is a collection of points on that open parabolic arc, okay, and this set intersects a given one simplex for some positive integer, and the intersection of these two sets is 1 over m comma 1 over m squared in R2. Okay, so you have to set them equal, and the solution is x equal to 1 over I. So if you plug in x to be equal to 1 over I, well, uh, it's not going to intersect this guy if I is different from m, first of all, okay. Right, so I has to be equal to m so that these two sets intersect each other. For that, one has to have I to be equal to m. And that in that case, we have 1 over m to be equal to x, and so if you plug in x to be 1 over m here, you get 1 over m comma 1 over m squared, this point. So this is the intersection of these two sets, right? Right. So 1 here, then you have 1/2 1/4. Okay, so probably this one a little steeper. So here, say 1/2 1/4 is here. Okay, so these points, these are the intersection points, and which are given by these ordered pairs. Okay, good. Now let me erase this. It is easy to see that for a given value of m in the set of positive integers, the singleton one over m comma 1 over m squared is closed in the one simplex x comma x over m in R2 such that x is non-negative. Okay, so this is a one simplex for a fixed m. Okay, you vary x, and what you get is that line segment, which is a one simplex. And this, so this is a point. Okay, this is a point lying on that one simplex, and this point is closed here. In subspace topology, induced from R2. Okay, In other words, the set 1 over I comma 1 over I squared in R2 such that I is a positive integer has a closed intersection with the one simplex given by this ordered pair okay. So this set has a closed intersection with this guy, okay. And it happens for every m being a positive integer, okay. Hence the set 1 over I comma 1 over I square is is closed. This guy is closed in mod K. Closed in mod K. Okay, this is what we proved. Now one sees that if you take all these pairs, ordered pairs in such that I is a positive integer, this this guy, okay, these points are is a subset of mod K. Mod K being the union of the one simplices given by this set of all ordered pairs x comma x over m in R2 such that x is non-negative, okay. So if you take this set, then this set is going to be a subset of the union of such one simplices, right? It's immediate with m being in the set of positive integers, okay. So if you fix m, you get a one simplex. If you keep varying m in the set of positive integers, you get all these one simplices, okay. Good. Hence this set of all ordered pairs of this form okay intersected with mod K, the union of all such simplices, okay. As you keep varying m, the intersection is equal to this set because this set is a subset here. So we get back this set And we know that mod K, which is the union of all such simplices, one simplices, okay, is being a subset of R2, and the set 1 over I comma 1 over I squared being in R2 such that I is a positive integer, and the set is not closed in R2. Why? It is not closed in R2 since the accumulation point or the limit point of the set is not included in this set. The accumulation point of this set is 0, 0, and 0, 0 is not here in this set, and hence this set is not a closed set in R2. Okay, good. So so we immediately see that the set, this set so uh, this guy is not closed in R2 because it does not contain its accumulation point. It is not closed in R2, and this can be written down as an intersection of these two sets. So it implies that this set is not closed in mod K, the union of all those one simplices in subspace topology inherited from R2. Okay, good. It's not closed in K in subspace topology, but it's closed in the defined topology on mod K. All right. Okay. All right. So now I'll take a break at this point, and I'll get back in the next segment with the definition of abstract simplicial complex. Thank you for attending this third segment.